Okay, this will be the last video set of examples for Chapter 6, and this time we are going to investigate a couple things with power. Okay, so in the first problem, let's think about having a jogger and they're running up some kind of flight of stairs or hill or any kind of incline. We don't really care about what the angle is, we really just are worried about how high they get to investigate their power. So the first question is just what is the jogger's power if they weigh 60 kilograms? This is how high they go, 4.5 meters. And it takes them 4 seconds to do that. I think the time really matters here. That's going to affect your power a lot. Why? Because power is just, you can think of it a lot of ways, but it's always got time involved. It's like work per time or energy transformed per time. There's usually a time component in the way you think about power. Okay? So I think we're going to probably do work per time. So let's just write that out. Let's say power equals work per time. That's one of the ways to think about it. The work that's being done, I think, is just equal to, if you look at the formulas, mgy, because you're just fighting gravity in this case. And we already even have the time. They said they did this in 4 seconds. We can put a nice 4 under there. And mgy should be easy too. So you get 60 times 9.8 times, how high did they go? 4.5. There we go. There's the jogger's power. So remember, if you have it all in standardized units, the SI unit for power is watts. And hopefully you answered the reading guide question about that. You know where watts came from. This guy named Watt. Watts, since they're having to do with, they can also have to do with electricity and other forms of energy. So just keep that in mind because they're going to come back later on. That's all I wanted to say about that. Anyway, there's the power. Let's turn that into horsepower because a lot of you probably have an idea of what your lawnmower is in horsepower, probably 2 or 3 horsepower, and cars and everything are always measured in the English units as well. So if we go 660, 746 watts is 1 horsepower. So this is, let's say, approximately 1 horsepower. Not quite, it's just under 1 horsepower. So this jogger is actually moving up that hill with a power of 1 horse. If you think about that, that's pretty amazing. The thing about this is that you got to realize is, well, of course, a person can't match the power of a horse unless they do it over a very short time interval, like 4 seconds. They couldn't maintain that same power ratio. Any person in the world couldn't maintain that same power ratio for a very long duration. So that's one thing that you got to think about when you're, otherwise you might say, well, this just doesn't make sense at all. How could a person have as much power as a horse? Well, they can. It's just only over the very short term. So how much energy was required? Since they're working at 1 horse, I'm betting it's a lot of energy. So remember that another way to think about power besides work over time is power is energy transformed. So kind of like change in energy or energy over time. So if you want the energy, I think you just multiply by time. So you get 660 times that 4, and that gives you the energy in joules. So what is that? That's 2,600. So that's 2,600 joules. Okay, well that was pretty easy. Maybe I didn't even need to do that one. Let's look at 615. I think we probably definitely need to look at this one. Okay, so in 615 we're talking about cars in relation to power. So we've got a car, it weighs 1,400 kilograms, it's going to go at a constant steady pace of 80 kilometers per hour on a 10-degree hill, and the answer is what power is required to do that and actually move. So we're going to have something about the retarding motion, like what is trying to stop that car. And I think that's a combination, we'll just assume it's 700 newtons, but this 700 newtons, the retarding force, what's that a combination of? That's like air resistance, if I can get that down, air resistance, and friction. Now remember, there's also a friction on the tires when its engine pulls on it that helps it move, and that's how the car is actually able to move by force, by friction. We're talking about the friction that's trying to hold it back. So you can see my little free body diagram here. You've got the force that we're trying to figure out, the retarding force, including friction and air resistance. Then you've got the normal force, like always, and gravity going straight down. So before you jump into this and try to get the power, remember, I think a few times I've done this now where I show you this rotation trick. Now if you look in the book, they're not going to do this rotation trick, and you can kind of just memorize how to do it, whether it's sine or cosine if you have an inclined plane, like this one. I prefer to rotate it so that it actually makes sense trigonometrically to me. Cosine being x, sine being y, etc. Anyway, so I kind of rotated it around this way. Yeah, let me get it. Yeah, I've got blue. I kind of rotated it this way, 10 degrees, so that it looks like this. Now you've got the normal force going straight up. Here's the retarding force. Here's the force we're trying to find, and there's gravity going at its angle now. Now, why did I say this is 80 degrees if that's 10 degrees? Well, it's because this is 80 degrees. If you look at this little triangle right here and blow it up, I guess we could do that up here. So if you blow up that little blue triangle that I've drawn, this is 10, which means this has to be 80, right? Because this is right angle. So if you just rotate that a little bit, you can see that that's 80 degrees. And now it should be pretty easy to figure out the force that we want over here. So Newton's law says that, Newton's second law, I should say, says that we're going to have exert a force equal to the sum of the retarding force. And, now, let me say that again. The force we're going to have to exert is going to have to equal that retarding force plus whatever gravity is doing in that direction in order for us to overcome it. So the retarding force that we assumed was just 700. And then gravity, you can see, is right here. If we want to go look at this component right here, then that's going to be the magnitude times the cosine, since we're looking at the x direction there, the cosine of 80 degrees. And that's not too bad. So you add those two up, and we've got to exert a force of that much or more to get moving as the car. So we plug in, we get 700 plus the mass of our car was 1400. The units are all good, times 9.8. Make sure your calculator's in degree mode. And what do we come up with? Let's see. These significant figures, I think it's about 3,100 newtons. Okay, there's the force. Now the question is, remember, we're trying to get power. So let me erase part of this junk. So there's the force. Don't lose track of your focus here. You're trying to get power. Remember, power can be expressed lots of ways. In the previous example, we said it's work divided by time, or energy divided by time. And if you look in your book or elsewhere, you're going to find there's lots of other expressions for power as well in different situations. You can change let's see, you can change work divided by time into, well, what's work? It's force through a distance divided by time. Then you've got distance and time, and you can say, hey, isn't distance rate times time? So if you simplify and do a little bit of simple algebra, you get rate times force is another expression for power. So notice I've got F and V that I'm working with here, so I'm going to use that one. The velocity they just gave to us, but I think we need to do a unit conversion, so I don't know if you guys need to see that by now. I guess I'll do it one more time. So kilometers, you know, I don't really want to do that. This is going to take time. So you look it up on the internet, or you do it longhand if you have to, for like the AP exam or my exam. Anyway, 80 kilometers per hour, we need meters per second, right? So that's going to be 22 meters per second. So then we plug in and we get 3,100 times 22. And that'll give us our power. Let's see, I got about 6.8 times 10 to the fourth. You convert that to horsepower if you want. So about 91 horsepower. Either one of those would have been fine for me, unless they said to do one specifically. Okay, now let's do something else. That same situation, let's imagine that we're already out driving and we pass another car. And we have to accelerate from 90 to 110 kilometers per hour in 6 seconds, and it takes us 6 seconds to do that. What power is needed for that little acceleration? So first, once again, I have to change these into meters per second. So you do that. There's the meters per second thing. So they said accelerating from that to that, so I better do the final one minus the initial one. It took 6 seconds, so the average acceleration is going to be 0.9, excuse me, 0.93 meters per second squared. They didn't ask us for the acceleration. Remember, we're talking about power. I think we're going to use this force times velocity thing again here, though, first. So first we've got to kind of figure out what the force is. So once again, we're going to use Newton's second law, where the sum of the forces in the x direction is equal to ma in the x direction. Sum of the forces, once again, I think we're going to have the retarding force subtracted from the force we want. And now we're going this acceleration, so we can plug this guy right in for a. So the mass of the car was 1400. This is how we're going to be accelerating, and we've still got to overcome that 700 newtons that's trying to pull us back just with air resistance and stuff. So that's the force we need, and I think it's a lot. Well, I guess it's not really more this time. It's 2,000 newtons. Because we're already going. I guess if that makes sense. I mean, when you accelerate, when you're in think about it like this: when you're in your car and you're driving around town, don't you consume more gas? And that's because you're having to exert more power to stop and overcome friction when you're just getting going in your car. If you're already going on the highway and you pass a car, I don't think it takes nearly as much gas or power, hence, to do that. So that does make sense. That is less than that. That makes sense to me if I think about it for a second. Anyway, so that's the force. So again, power, we just said, was force times velocity. So force times velocity. The question is, what's our velocity here? Well, we are going from this to this. So if we're accelerating from there to there, then that implies that's a little bit sneaky, but that implies that this is the velocity we'd need at maximum. So this is, just kind of an estimate. So I guess we use that velocity, because if we use this velocity, we wouldn't be going fast enough, and it wouldn't encompass the whole trip. So this is the biggest velocity, so hence the biggest power we're going to need at any instant during that little maneuver that we do. So let's see what we need here. I'm still thinking it might be less than what we needed to start. Yeah, my calculator says 6.12. It's a little bit less, right? And that's about 82 horsepower according to the book. So yeah, that is still a little bit less executing a maneuver like that than just starting your car and overcoming the force of friction due to gravity and so forth. So anyway, hope you found that illustrative, and ask me any questions in class when we go over the reading guide. Bye.